In this video, I am going to be talking about multi-threading, execution policies, and use of execution policies in STL algorithms. And first, let me talk about multi-threading. Multi-threading is the way of designing a process so that it gets executed in multiple threads. You can see the process as a process is essentially a program in execution. A process, the outer rectangle represents the process. Inside the process, there are multiple vertical bars which represent multiple threads. Similar tags is actually, if the task is similar and it is to be used for different purposes, then it can be set to be executed in multiple threads, and they have to be list dependent with each other. There should be list amount of data sharing with each other. They should essentially be executed independently of each other. In this picture, TS1 is one thread, TS2 another thread, TS3 and TS4. There could be many threads, maybe 10, 50, 100, depending on the requirement. The process of creating a new thread out of the main thread, the process itself is a main thread, and the process of creating a new thread is called spawning. Spawning is a process which results in a new thread or child thread. So in this case, this entire process is going to be main thread, and TS1 is one child thread, TS2 another child thread. And once these threads are executed, and the main thread actually waits all the threads to get executed. So that process is called synchronization. It is a process whereby the main thread actually makes sure that all the child threads are executed, and after that the outcome of that execution is combined to be used for the further execution of the process. This is multi-threading. Now let's talk about execution policies. Execution policies are the types with which are actually defined. These are the classes, types defined as classes, which are defined within the namespace called execution, std execution namespace. And these are the forward declaration of the classes: sequence policy class, parallel policy class, parallel unsequence policy class, and unsequence policy classes. And in the same namespace we have the instantiation of those classes. Sequence policy instantiated to the object of type SEQ, and parallel policy class instantiated as an object with the name PAR, and parallel unsequence policy is instantiated with the name PAR underscore unsec on SEQ, and unsequence policy is executed with the name on SEQ. So these are the policy, the sequence policy, parallel unsequence policy, and unsequence policy are policy types, and this SEQ, PAR unseq are policy instances or policy objects created out of those types. So now I'm going to switch to the coding to explain it a little bit more. So I have this editor which I'm going to use to explain it further. The policy instances or policy objects are to be passed into the STL algorithms to the STL algorithms to suggest to follow So when you say policy instances object, the name of these instances are seq for sequential, PAR for parallel, PAR underscore on SEQ, and on SEQ. Right, for example, we have a, let's consider the STL following STL algorithms. This is one algorithm. These are among the popular STL algorithms. Find if, count if, copy if, std transform, etc. These are the STL algorithms. In regular execution of these algorithms, you would pass the first iterator of the container, like this, and you have some logic to apply into it as lambda expression. So this is the if the vector contains integer, then you will have integer x, and then you can have some logic here. So this is the style you would use for this algorithm. You know, because I had this closing characters for the comment, so let me just avoid this. So I want to keep it like this. Okay, now this is the logic you would use, and similarly for find if, in all cases you may have in the case of find, you can have an object, and in find if you have logic, count you can have object, and count if, copy. In the case of copy, I think you need another thing here. In transform also you need so this is the way you are actually using this STL algorithm. But in the case of policy, if you want to apply policy into it, then you need to have the first argument as a policy here in all these cases. Right, so if I want to execute this for its by following the parallel policy, then I would pass the policy object par as the first argument. If I want to execute this find as by following the sequential policy, I would pass sec object, again par parallel policy, and so on and so forth. So this is how you run this algorithm. So to enable this policy execution, policy, you must include a library called execution. So with this library, in the previous version of the compiler, this library may not be available. So if you are not able to use it, make sure that you update your C++ compiler to the most recent version. If not available. Right, so this is how you use STL algorithm with the policy, and this policy based algorithms were actually introduced in C++ 17 standard. In 2017 many updates were made to C++ standard. Okay, so if you use the previous version of the algorithm, then you may not have available this policy. User policy for STL algorithms may not be available. So you need at least 17 version to run this algorithm with the policy as the first argument. Now let me talk quickly about these different policies. We have this is a class, and for this using this policy actually suggests, let me only use sec object. So this policy suggests the algorithm may not be parallelized. And passing this pair object suggests the algorithm may be parallelized. Maybe in this case it may be parallelized or vectorized. These are the vectorization and migration across thread are the concepts that I'm going to discuss in the end of this video. So if you want to know about this, stay on till the end of the video. By the end of video, or if you just want to listen what I tell you about this, you can switch to the end of the video and try to find out where I actually talk. Then on sequential policy, it suggests that it may be vectorized only. Actually not algorithm, but algorithm execution, right? So these are the different purpose of using this policy objects. Now I'm going to start coding and showing you how to do this actually in coding. So for that I want to create let me have a size of a vector defined to be, let's say, 500,000, and a vector, sorry, an array. Sorry, just to correct, this is size of array, and I want to use this to specify the size. Now I want to populate this array with random numbers, right? So to populate a random number, I want to use STL algorithm. So the most easy algorithm or most convenient algorithm to be used in this case is going to be for each. And in the for each, I want to pass first thing I want to pass in this algorithm is the address or iterator of the first item element. So the address of first element and address of last element. I mean, this is the address, not the address of last element, but this is the address of address next to the last element. So, and the lambda expression logic. In the lambda expression logic, because this array contains integer type, so I want to receive integer, and I want to make changes. I want to set the random values into it. So for that reason, I want to receive by reference, and x equals to use random function, and I want to set the value set to it in the range from 0 to 100. So this is the logic I'm using here. So this will actually set the elements of this array to some to random integer values in the range from 0 to 100. Now I'm going to see what actually the elements array actually has content the random values after execution of these lines, this code. So for that, let me use copy. I want to copy some selected elements from this array into the output stream so that it will get printed. So I want to copy first 10 elements to O stream iterator for it is for integer type, and the parameter we pass is going to be cout, and the delimiter I want to actually delimit the items. I want to separate the displayed items by comma, and also I would like to display the last 10 items. And I want to display these things in different lines. Right. Let me try to attempt to execute this code and make sure that it works. Then I can go further from there. So I have this course. This main1.cpp is the file that contains that code I have placed. I'm going to use the g++ equals to c++. I'm using 23 standard. Output file main1.exe and source file main1.cpp. Now I have this main1.exe to be executed. You can see the first 10 data set to that array: 83, 86, 77, 15, 93. This is random number in the range of 0 to 100, and the last 10 data items are this one, integer items. Okay, this is working. So now what I'm going to do here is I want to run this same algorithm, for each algorithm, using the policies. So I want to execute this algorithm using the in sequential policy, and I want to execute the same algorithm using the parallel policy. So but when I execute using policy, I need to be able to see the difference in time, because the purpose of executing of logic using parallel policy is efficiency, right? If the computer has the way of executing the things in parallel, then that will allow the algorithm to get executed faster. So for that I need to have a way of measuring the timing. Time, I want to measure time here, t1. I want to measure time t2 and see the difference and display that difference. And again I want to measure t1, t2 and see the difference. A very useful tool to measure time difference actually comes through the library called chrono. And by the way, these algorithms we are using are actually available through the algorithm library, so we also need to include algorithm library. And also you should actually, this iterator is actually officially it is available through the iterator library. Sometimes if your compiler may complain, in that case make sure that you include the iterator library as well, right? So again, if your compiler complains the use of this OSTM iterator, then you make sure that you include iterator library on the top. So now the way I'm going to use a chrono library is first I will actually measure this T1 as the current time stamp, high resolution. So it will actually check the current time and copy that time into T1 variable, and I want to do same for T2. Right, and after that I need to see the duration. I need to compute the duration. Is equal to std chrono duration and double it will take duration in microseconds, in this case micro, and T2 minus T1. So it will compute the duration, and I can display this duration time taken by sequential policy execution is going to be duration count. So this is this will actually display the time. I want to avoid typing entire thing, so let me copy and paste. And since T1 was already created in this place, so I didn't need to define again. Obviously, if I do define, then it will compiler will actually complain. So we have T2 and duration, and we have this is for parallel policy. So now what it should display is the time taken for the execution of this logic, this algorithm, by following sequential policy and by following the parallel policy. Okay, let me see the output of this code. Compile and see the output. Compile and execute. So we can see the time taken. I think I need to do a little bit formatting here, because the time taken is displayed this on I want to display this on the next line, sequence policy. But you can see the time taken by parallel policy is 23 millisecond, 2304 millisecond, and it is 2549 millisecond. So going back to the code again. So after I display all these things, I want to insert new line character. So compile it again. Execute. So I can see in this case it's 29 to 22. So it looks a little bit odd, because we expect the parallel execution to execute faster, if I do this execution multiple times, then this is I mean, there's a big question mark, because in all three executions the parallel policy is required more time, but which is unusual, I mean not expected. This usually happens when we have the problem which is not well suited for parallel policy. Okay, because to get advantage of parallel policy, you need to have a problem which is suited. For example, if you perform execution, but which is very, to compute to execute parallel policy, there is some amount of overhead that is involved, right? You need to distribute things in parallel, and in sequence policy you don't need to distribute. You just put the thing in the processor, it will compute and get the result. But in the case of parallel policy, you spread things out in multiple execution units, and then that spreading out actually takes some overhead. So if the problem is not suited, then parallel may offer you require you more time, so it will be not advantageous to use parallel policy. So let me make some changes. I'm gonna add some nonsensical kind of code here. X equals to x plus something that doesn't make any sense, but just I want to make sure that there is a little more amount of computation that is involved here. 2 minus 2 plus 2. So I'm going to be just putting this, just removing, subtracting 2 and adding 2 in a kind of sort of a nonsensical way. Entire the result of this entire evaluation is going to be essentially 0. There's not going to be any change, but the purpose is to add some to include some computation inside in the logic in the both sequential execution and parallel execution, and try to see what whether that actually makes any difference in terms of the amount of time taken. Compilation, execution. Now 27, 26, again execute one more time. 26, 25. So still there is a problem. Okay, switching back to the code again one more time. Maybe let me reduce this code a little bit. Now you can see this is constantly a kind of, in this is an exception, but constantly most of the time it is more parallel is required less time. By 26, 34. So if you compute the average of total time required, in this case sequential policy execution has required more time than parallel. The main thing is you have to have a right problem to be executed using sequential and parallel policy. If a problem is right for parallel policy, then it will offer advantage. Okay, so that is the main message you should take from here. And in addition to this sequential and parallel policy, I can also demonstrate, but I don't think similar to this situation, because if the hardware supports this policy execution better, then it will offer advantage. If hardware is not well designed to support this policy execution, and also the problem is not of right choice, then you cannot see the difference. But anyway, I'm gonna demonstrate show you how to use parallel on-sequence policy, pass on-sequence policy object. This was sequential, parallel, unsequential, and I'm going to pass on sequence policy here, right? And this is parallel on sequence. Right now, this unsequence policy is it is flagging an error. Because this compiler is associated with a previous version of C++ standard, so this was a recently added feature, but I'm using a 23 compiler, so when I compile this is that compiler will not actually flag this as an error. Okay, so let me switch to the compilation. Execution. Now we can see the time taken by parallel policy, sequential policy, and sequence on parallel. One more time, right? So the advantage of this policies will be clear when you have right choice of the problem and the right platform or the computer that you are using to execute the algorithm. Okay, that is the message I'm going to pass here. And next I am going to talk about the term called vectorization in a bit more detail, right? And migration across threads. Vectorization, migration across threads are actually the ways that are suggested by this parallel on-sequence policy to be applied. Parallelization, vectorization, and migration across threads. And vectorization is the policy that is actually suggested by this on-sequence policy. So it's really important we understand this vectorization and migration across threads. So to explain it, vectorization is a process of executing multiple at the same time or in parallel on the computer or platform that supports this parallel operation. For example, many core kind of on in many core type of processors, right? For example, one example I want to give to explain it better is for example, if I have three vectors, three arrays. One array is integer type array with the elements 1, 2, 3, 4, and so on. Total 100 elements. I have another array 51, 52, 53, and so on. Again, total 100. And I have another element of 100 elements. The task here is I want to copy, perform addition on the elements of ARR, BRR, and copy that result into CRR. For example, I want to add 1 and 51 and store that in the first element of CRR. I want to add 2 and 52 and store that in the second element of CRR, and so on and so forth. So for that basic iteration loop that you are going to use is going to be for loop in C++, I less than 100, I plus plus, CRR I equals to right. Now the vectorized version of this operation would be something like this. I want to do vectorize operation, so that 4 of this computation, this addition and assignment, are actually performed at the same time simultaneously. So for int I equals to 0, I less than 100, and I plus equals to 4. I want to step by 4, and inside CRI equals to I plus I plus 1 equals to I plus 1 plus BRRI plus 1. Copy and paste. I plus 2 So this is the simulation. You can consider this as a simulated version of the vectorize operation. In one iteration, 4 operations are carried out, but if you run this algorithm in the regular non-vectorized way, this will be carried out one by one. Therefore, the performance of this second loop and first loop is going to be same. There's not going to be any difference. But if the computer on which you run your program supports this vectorized operation, or this kind of parallel many core kind of processing operation, in that case you may have a single instruction to design to carry out all these 4 lines of code instruction. For example, we can have code something like this, and we can have vector. So we can have something like this. This statement would be vectorize operation 4 elements, could be different name, and I would be passing the address, passing as a pointer, so that I need to this operation actually needs to access the address, and it will actually access the 4 elements of all these arrays. Beginning from I plus 1, I plus 2, I plus 3, and it will at the same time it will spread the computation in 4 different cores, so that the computation actually takes place at the same time in as a parallel operation. So you can consider this as a one single instruction happening. So this is called the vectorized operation. So if the process supports, again, then this operation offers advantage, but if process doesn't support, then it can be extra overhead using this kind of implementing this kind of operation. And the next thing I want to discuss is migration across threads. So when a thread is executing, let me go back to the slide and go back to this diagram. So the process, when this thread 1, thread 2, thread 3 are being executed, they have their own variables stored in the memory space, which actually amounts to the context. All data, everything that is needed for this execution are actually placed in the memory, which is a context. And if for example, if you want to, if this thread 1 is being executed and you want to switch this, let's say suppose thread 1 is being executed, it is using one core of the one CPU, and you want this execution to be switched to another different core, right? So in that case, the entire context has to be copied and actually transferred to the different core execution. So that is the context transfer, context copying. So those kind of operations, migration across thread is migrating all the entire thing that are necessary for a thread being executed to different the place of execution. So this is the process, and actually the that this is the process of migration, and this pair on sequence policy actually suggests to apply that sort of migrated execution if that is possible. And also it suggests the vectorize operation, and it also suggests the parallelize operation. Okay, so this is the end of this video. Thank you for watching.